Hello and welcome to the second part of this webinar series that is jointly organized by Friendship Systems and SimScale. My name is Matthias Brenner and I will guide you, like the last time, through this webinar on the side of Friendship Systems. And this time we have Alex Fischer who will take care of SimScale side. Hello, Alex.
Hello, Matthias.
The title of this Hi. The title of this webinar, as you can see, is Simulation-Based Design of Complex Geometries using CAESES-free and SimScale. And this means that apart from introducing you to the two systems that are involved here, we are presenting a simple workflow that allows you to make use of the free version of CAESES on the one side, as well as the free offering from SimScale on the other side, as CAE tools in the development process of your products. So last week we have started demonstrating this workflow on the example of a cooling fan, which we will further explore today. And this example, as most of you have probably seen already, is also available to you for your own exercises, and we will say a bit more about this later on. Two final notes this time before we get started. If you missed the first time of this webinar last week, you can find the video recording on our or on SimScale's website, so you can catch up. And also another announcement is that we will not have a dedicated Q&A session at the end of this webinar, so as in the last time, you're welcome to post your questions in the GoToWebinar chat and we will follow up afterwards, or you will also have the possibility to ask questions afterwards in our respective forums. So let me introduce ourselves a bit more. My co-host Alex is a co-founder of SimScale and currently holds the position of product manager there. He has a background in mechanical engineering with a focus on computational mechanics. Fittingly to the company he's working at, he's very excited about new trends in the simulation industry. I'm currently head of sales for Europe at Friendship Systems. I've been with the company for about 8 years now and have previously worked in the pre-sales and engineering team. My original technical background is in naval architecture, but over the years by now I have worked on many geometry, parametrization and optimization problems in quite a lot of different fields of the engineering industry. So what do we have on the agenda for today? First of all, we will do, let's say for the people that were not able to attend last week's webinar, we will just have a very brief presentation or recap of Friendship Systems and CAESES and SimScale and their computing platform. For those of you that already heard that last week, bear with us. I promise it will be brief. And then I will again show shortly the case that we're working on. And this time I will, let's say, go into a bit more detail related to the modeling of our test case. And also I will show how to do an automated geometry variation using CAESES. And then Alex will tell you how to set up the simulation in SimScale and give you a little bit of background about the type of simulation that we will be working on. So this time, in difference to last time where we focused on aerodynamic aspects, we will take a look at structural aspects. And finally, we'll have a wrap up to end up this session. So, as I said, let me give you a quick recap if you're not familiar with CAESES and tell you what CAESES is about. So CAESES is a CAE platform. The name stands for CAE System Empowering Simulation. That's the acronym behind CAESES. And the intention of CAESES is to provide the functionality that is necessary in order to run simulation-driven design. So developing your geometry design based on simulation results and enable the user to carry out optimization processes, automated optimization processes, as well as design explorations. And to develop the product he's working on to get a higher performance, and obviously through the automation of the process save time and money. So what is included in CAESES? You can basically see in the picture that is shown here. So CAESES includes as a first and probably most important part its own CAD kernel, which is a very, let's say, specialized CAD tool, very focused on providing geometry that is ready for simulation, that is the type of geometry that is needed for the simulation. So we specifically don't go into the whole PLM process of manufacturing and so on, but we focus on the geometry that you need for the simulation, and we provide it in a way that you don't need to do cleanup or too much pre-processing in order to use it in the simulation. Another important focus of our CAD modeling is that we build up the geometry in a way that it can be very easily changed and is suitable for automated variation, which is often a bottleneck with, let's say, more traditional CAD tools that either don't allow very simple ways of varying the geometry or lack a little bit the robustness that is necessary for an automated variation process. So that's the CAD part. We have connect to external simulation software, so we don't have any included simulation within CAESES, but we offer a generic interface where you can couple different types or arbitrary types of simulation softwares. In the process that we showed last week and also we're showing this week, we will have a bit more of a manual interaction between the two systems of CAESES and the simulation by transferring the geometry from one to the other. But we are working on making a tighter integration between our two systems, so that we hope that in the future, maybe in our next webinar, we will be able to show you how to run SimScale simulations directly from within CAESES. The final component that is included in CAESES is the optimization part. Here we provide the algorithms and the post-processing tools that are necessary when you want to run design explorations or formal optimization. One more thing I would like to point out here, since this webinar is focused specifically on CAESES free users, so the users of our free version, these green lines in the picture show you the parts that are available within the free version. So basically all of the CAD functionality and the connection functionality to simulation software are available in CAESES free, with a few very small limitations. And the optimization part, on the other hand, is excluded. So with CAESES free, you're not able to run, let's say, these automated optimization processes. The kind of geometries that we are typically working on with CAESES can be seen in this slide. So as an example, we have ship or boat hulls, powertrain components, turbochargers, propellers, and other types of turbomachinery like turbines, gas turbine, hydro turbines, steam turbines, fans, as we will see also later on in the webinar, and valves. So much from my side as a short recap about what CAESES is. Now Alex will take over and give you again also a small recap about SimScale, and then I will show you a bit more details about the modeling of our fan.
So, thank you, Mattia. Welcome also from my side. As Mattia already introduced me, I'm Alex. I'm working here at SimScale in the product department, actually caring for what SimScale is heading to, what is our objection, what we want to focus on, and that is also what I want to introduce SimScale here right now in the beginning. It was already mentioned last week by our presenter Pavel Sosnovsky, so I don't want to spend too much time actually presenting this to you, but just that the basic concept is clear. I want to say some words about it. So SimScale is a quite new company. We were founded around 4 years ago, and actually we had that vision that SimScale wants to bring simulation to everybody in the engineering world and make it available to everybody. So simulation is around for a long time right now, and it's also used for a long time, but not by that many people that actually could use it already and could take advantage of using simulation. And that is basically due to some factors that we actually want to address, some barriers that we simply want to remove, and we always count them down to 3 important ones, which is actually the accessibility. So in general, when you run simulation, which is quite computation intensive, you need quite some hardware, actually, computing stations with a lot of cores. Actually, you need the software. You have kind of software licenses for your workstations, and for all of that you need the technical support, you need updates, you need to install the software first. And with SimScale we want to go with a different approach and make it easier accessible by simply using a web browser, putting the complete interaction into this framework, which is accessible to almost everybody in the world, and address the part where the computation intensive part comes in by actually adding high-performance computing in the cloud, which is then actually taken from the computers of our users, and the computationally intensive parts are done there. And that's simply how we want to get it out to everybody. And the only thing you basically need to get started is to have a web browser installed on your computer and have a fairly okay internet connection. So, and the second part is that simulation software, it's a complex product. It has been around for quite some time, but for most of the parts it's quite expensive, and you need to pay the license fees actually often for the seats of at your computers, that you have 4 cores available, or you have to then increase that by buying a better license. And for us, it's simply that we say, okay, the base part should be available to everybody, and that's what we want to achieve. And that is why SimScale, the basic functionality, is available to everybody for free. So you can just start your browser, go on our website, create an account, and you can basically start without a need to pay anything or to subscribe to one of our plans. But there's one thing that is really related to the fact that we have a third barrier, which I will speak about in a second, that we actually want to address. The people share the knowledge when they do this. So you can do everything for free, but by doing that, what you do is publicly available for everybody. And we want that everybody contributes by doing this for free to that knowledge that is then built in this community. And if you don't want to do that, if you're doing your industry design, which is of course also a very important part of our business model, then of course you don't want to share your stuff. You don't even want people to know that you're working on a certain thing. So then you simply can do a subscription-based plan and start off with the same functionality, but everything is private for you, and you still have access to the knowledge base and to the help and support that is provided by our community. And the last barrier, I already mentioned it, is this barrier about that simulation. It is a complex product. It is complex to do the simulations you want to need, but actually you have the expertise of what you are interested in as an industry partner. So you want to find out actually how now to get this done in a simulation context, and that is what thousands of engineers already did in the SimScale community. So what you should do is actually go to our public projects, search if somebody did something similar to what you actually want to achieve, and take this as a template and start from that. And this is basically what SimScale is about and what we want to achieve. And I will not spend any more time on describing that, but give you simply in the first 2 minutes when I show you the case that we want to look at afterwards, simply what that is about and how you can find those public projects. And because of that, I will give now the presentation mode back to Mattia, and he will give you now an introduction to the modeling details in CAESES.
All right. Great, Alex. Thanks. So let me again give you a short introduction into the specific case that we are looking at in this webinar series. The geometry is an axial cooling fan with 6 blades and 100 millimeters of diameter, so something that you would typically find in your PC or other electronic devices for cooling. Last time we looked at some design targets and let's say properties that were related to the aerodynamics of the system. So we wanted the fan to produce a high airflow to increase the cooling performance, and also at the same time we need to take care of the torque that the fan needs to produce this airflow, so that we can reduce the energy consumption or maybe have even a smaller electric motor. This time we will look at slightly different aspects, so we will focus on the say structural aspects. Alex will show later on how to do a frequency analysis that will give us some indication of related to the vibrations that are affecting the fan and maybe the noise that is generated. So on my side, I will now go into a couple of more details about the modeling. So last time, you might remember we talked about the so-called meta surface, which is this special type of parametric surface that we use in CAESES to model complex geometries. And you might remember I told you last time the meta surface is built up of basically 3 steps. We start the design by creating a parametrized definition of the cross-section through the surface. The second step is to define how the parameters of the cross-section change in the direction of the surface and describe these changes with distribution functions, and then we connect these 2 informations and are able to generate the surface. So now, as a first step, I would like to go into the first part of this meta-surface modeling. So we saw last time already which parameters have been used to describe the cross-section of the fan blade, but we didn't really talk in detail how this is done in CAESES. And yeah, to show that, I would like to switch over to CAESES itself. Let me open this blank user interface. And what we are using for that in CAESES to describe this parametrized cross-section through the surface is the so-called feature definition. And the feature definition is something that can basically be compared a little bit to a script. So you have certain input, in this case the parameters that describe the cross-section, and then you use this input to produce a certain geometry, and the geometry objects that you're creating within the script is the output of the feature. So let's see how this looks like on a very, let's say, very simple example. If I go to the feature menu in CAESES, I can create a new feature definition, can give it a name, let's say straight line. And now, as a first step, I have to describe the so-called arguments, which are the input to my feature. So let's say I want to have a double value for the length of my line. I give it the name length, a default value, and now I can go in my create function where I can, let's say, program in our own scripting language what should happen with this input. In this case, I want to create a line with the name straight. Let's increase our font size a little bit so you all can see it better. So we create a line with the name straight, and the line should begin at the position 0, 0, 0 in the origin, and it should end at the position length 0, 0. So very simple feature, that's it. Input is the length. The script creates a straight line using this length value as an input. Now I can apply my feature, this saves it, and in the attributes, this is the output of the feature, I can see my object of type line with the name straight that they created inside of the feature definition. So now I have defined my feature, and I can use this template, so to say, to create a feature object in CAESES. And you can see now I have an object here in my tree that shows the input that I defined in the feature definition length. Here in the 3D view you can see the line that has been created, and if I change the length, the line will change its length, surprisingly. Alright, that's so to say very short introduction how these feature definitions work like. You may ask yourself at this point, how do I learn the scripting language? Maybe it's difficult to write more complex things. So another thing I would like to show you is that you can also write these feature definitions without any knowledge of the scripting language whatsoever. So rather than writing the feature definition from scratch, as I did, I would just take my model, create a parameter here, give it the name length, a value of 1, and then I create a line, and the start position of this line is 0, 0, 0. The end position is length 0, 0, and this gives me the line. I give the line a name, straight, and now let's assume I have created this model in my model tree in CAESES, and I think I would like to reuse this, or I would like to use this as an input for a meta-surface generation as my cross-section definition. You can simply select what you created, except for the objects that you want to use as input, and create a feature from selection. So I select just my line, not the parameter length, because this should be an input, create a new definition from selection, and as you can see, CAESES automatically creates a feature definition with an input of type double, the name length, which is the object that we did not select. In the create function looks very slightly different to what I had, creates line and sets the start and end position, but the result is the same. I have my line straight. So this shows you that you can also create these feature definitions without knowing anything about this scripting language that you need there. So this was a very simple example. Let's take a look at our fan model that we were working on last time, and see how the feature definition for the cross-section of the fan blade looks like. We have our feature definition for the section here in the tree. You will also find it in the example project. And if we click here on this edit button or right-click edit, we can take a look at the feature text. And I will just briefly go through it. So what we do here is we create, first of all, we start with this thickness distribution of our section. So the section is based on a mean camber line and a thickness distribution. So the first thing we create here in the feature is the thickness distribution. We create the leading edge here we create, in this part, we create the trailing edge radius with another circle. In between these two circles, we create a so-called F-spline curve, which is basically a smooth connection that creates a tangent continuous connection between these two circles. This is our thickness distribution, so we put the two circles and the connection into a polycurve, and this is the final thickness distribution. Then as a next thing, we create our mean camber line. For that we use again a F-spline curve where we set the start tangent and the end tangent. These are parameters that can be controlled. The length is also controlled by a parameter for the chord length. And then in the next step, we use an offset curve to apply the thickness distribution as an offset to the mean camber line. So you can see that our base curve is the camber line. We set the thickness curve that we created before, and then we say this thickness should be applied on both sides of the mean camber line as we would like to have it. So this will give us the final profile shape in 2D. So now we can rotate this 2D profile by the pitch angle that we would like to have, and also we translate it to give it the correct position for later on for the 3D profile in axial and circumferential direction. And finally, we take our rotated, translated 2D profile and use a cylinder transformation to map the 2D profile onto a cylinder so that we get our 3D profile section that is then used for the blade generation. So this is in short what happens in the cross-section definition of our fan blade. The result is our 3D section. We can create simply an example of the section, which you can see now here on the screen. So we see here the 2D cross-section, and as you can see here on a radius, if I rotate it, the 2D section that has been mapped to a cylindrical surface to get our 3D section. Okay, now maybe we zoom in on the 2D section a little bit to show you. If I select my feature now in the tree, you can see all the input parameters that had been defined. So I can change things like the chord length, or for the mean camber line, the leading edge angle, or trailing edge angle, or let's say the leading edge radius, make it much bigger, or the spread angle at the leading edge. This makes the blade thicker. Same thing for the trailing edge. And so on and so forth. Maybe the pitch angle is something also nice to see. Yeah, so we rotate about the leading edge of the section. So what we have now is a fully parameterized definition of our cross section. If we create just a single instance of this feature, as we have done here, we can just enter, let's say, discrete values for our parameters here. But obviously, when we want to create a surface, we want to give a continuously changing value as an input. So we want to connect this feature definition to our distribution functions that maybe I can display again. So here we have our distribution functions. and we want to connect these here as an input to the parameters rather than a single value. And this is done by another object, which is the so-called curve engine. The curve engine object takes a feature definition and is able to supply continuous curves rather than single parameter values for certain parameters. And this curve engine, here it's called sections, can then be used by the meta surface object to create a surface in a specified range. So we go from 0 to 1, this is the normalized radius in our case, and we use our curve engine sections that will provide the shape of the cross-section at every position of the surface. We can also use different curve engines at the beginning and at the end of the surface so that we can create a blending between two different cross-section definitions. And that gives us our final meta surface, which maybe we can take a look at here. This is the meta surface of the blade. Yeah, you can see if I restrict the range, just have half of the blade. And this is the full range. Okay, I hope this gives a bit more of an input or information how a meta surface is built up. And now I would like to quickly show you how to create a variation, an automated variation of the geometry. Last time we saw a manual variation, so we created manual variants and changed some parameters by hand. This time I would like to show you how to do it in an automatic way. This is only possible, let's say, in a very limited way with the free version of CAESES. So this is maybe a little bit of an outlook into what the, let's say, pro version of CAESES can do. So since we are looking at structural things this time, we let's say we want to change some parameters that might have an influence on the structural strength or vibration behavior of the blade. So some things that I have in mind is to increase maybe the thickness at the root of the blade or to increase the fillet radius of the root fillet of the blade. Another thing might be, you see this blade is swept in the rotation direction. Yeah, in this direction we have a sweep in the blade, so maybe we can reduce the sweep a little bit. So these are three parameters just that I thought of we could change. So what I will do now for the automated variation, create a design variable for each one of these things. So the thickness that we want to control can be influenced, as you saw in the single feature I created, through the spread angle at the leading edge and at the trailing edge. So I will just simply take the spread here and multiply it with a certain factor, which is 1 now, and say this factor should be a design variable. Let's call it thickness factor at the root of the blade, and I'm going to apply the same factor to the spread angle at the trailing edge. Okay, this is the first design variable. The second one, as I mentioned, should be the fillet radius. So you see the fillet radius has an expression in it because we set it as a relative value to the hub radius of the fan. So I don't want to change this relationship because it gives us a nice scalability of the model, but rather, again, simply add a factor here, and this should be another design variable. Call it fillet factor. And finally, I would like to be able to influence the sweep of of the blade. So this is controlled here through this point. I can show if I reduce the value here, the sweep changes. So I would like simply to make this value a design variable. And let's call it tip sweep. Okay, now I have my design variables set up. Now I can create an algorithm, variation algorithm, to change these variables in an automated way. So I take my thickness factor, specify the lower and upper bound of the value. Let's say we want to go from 1 to 1.5 because we want to increase thickness maybe to make it more strong, the blade. And the same for the fillet factor. We set the range from 1 to 2. And the tip sweep, we go from 0.3, so reduce the sweep a bit, to 0.7. So these are the bounds for our design variables. Now I would like to create 5 variants, and also I would like to create some screenshots for the designs that I'm creating. So let's say we want to create a screenshot of our function distributions here, and maybe of our final fan geometry. So I can define this screenshot collection in a minute. So create a new screenshot collection. I want to create a screenshot of our 3D view where we have the complete geometry, and a screenshot of our 3D overview. This is the one down here where we see the functional distributions. One more thing that I have to do here, because for the analysis in SimScale we would like to export a step file for each of the variants that we create. So here, where I have also my screenshots, I will define a post-processing command to export the fan geometry. So I take the fan here, the fan object, and say, give a command, export step, and the step file should get a name, get design here. So this is the directory of every variant. I'm not going to explain this in too much detail, otherwise it will take us too long. We give the name fan underscore, and then we add get current design dot get name, and finally we add dot step at the end. So this command basically will export the fan geometry as a step file, and then this lengthy command that I used here is just to give it the right name and put it into the right folder. So we will have some objects with the name fan and then name of the variant dot step. That's it for the preparation. Now we can start the variation, and as you can see, CAESES will start to create design variants. I have, of course, prepared this already, so we don't have to wait for it. So at the end, we will see a table like this. We have created 5 variants that we can also see here in the table. And we can, through this button here, switch to the design viewer, where we can compare the screenshots of the variants that we created. As I said, the distribution functions and the geometry. We also have an interactive 3D geometry of the different fan variants, so that we can compare them also interactively. And maybe a last functionality here, we can export these pictures here to a GIF file, specify a certain frame duration, save, and if we go into that folder, we see the GIF that we created where you can see the variation of the geometry. Okay, that's almost it. The final thing I would like to show you is that if we go into the folder where this project file is located, we have a subfolder with the name of the project, and here you can find another folder with the name of the run, variation run that we executed, and here we have a folder for each variant, and this folder structure is created automatically by CAESES, and in every variant folder we find the screenshots that we defined, as well as, and that's the important step, as the name says, step, the step file of the geometry that was exported by CAESES, and this is, so to say, the transition to the next step in the process, which is to run this geometry in the SimScale simulation environment. So I will give back to Alex, which will show you how to run these computations.
Thank you, Mattia. So I will go back to my presentation. And thank you for pointing out actually this big benefit of CAESES, showing how you can easily create a lot of different designs that you actually want to test, because that is also what Pavel, I think, showed in the last session, that what simulation has as a benefit is as well that in this normal cycle of product development, where you would want to define a design, do a prototype, and then test it afterwards, and then you might recircle, check if everything is fine. You can now do this loop simply using your CAD and your CAE software, and circle on that beforehand, and it's much easier. And by having the possibility to automate this process both on the CAD side and on the simulation side, I think it's a great benefit compared to the usual or the old way of doing the testing and the development of a product. So I will show that in a minute when we go to the platform, but I think it's an important aspect regarding this. So let's have a look at the case that we actually want to present now, based on the geometry that we saw that Mattia showed us in CAESES. But as a quick first hint, simply the structural part we are discussing right now is based on SimScale on the finite element analysis, and we just want to show that there are just various physics and applications that can be simulated with this method. And that goes from static dynamic analysis over frequency model, heat transfer, coupled solvers. But we are going to look just as one representation of those solvers. We will look at the frequency analysis, and based on those I will at least slightly touch the harmonic analysis and modal dynamics, or the basics of those, as they are kind of based on the frequency analysis. We see here that actually a frequency analysis is used to determine the eigenmodes and eigenfrequency of a structure. So what is an eigenmode and what is an eigenfrequency? If you would see it in a mathematical point, and I don't want to go into detail at all, but this is a classical eigenvalue problem that you want to solve. But if you're interested in what does it provide me, what do I get back for the structure, this is simply if your structure would have no bearing, it would be just like it is. The natural eigenfrequencies would be the frequencies where your structure would do those natural eigenmode movements, which you can see here illustrated on the right for a very simple geometry. So this is simply kind of a plate. But it also provides very much information for more hands-on industrial applications and more hands-on problems, but we will see that in a second. I just want to mention that the base of those equations simply is the very basic dynamic equation for structures, where you would have here the mass matrix, you have the stiffness matrix K, the mass matrix M, which you could easily describe as the counterparts of, for example, the force that acts on a spring. If you would now compress the spring, you get some force dependent on the displacement that you apply on the spring. And with the mass, it's kind of the same. Everybody knows Newton's law, simply that dependent on the mass and the acceleration, you have a force, and those have to be an equilibrium. And if you want to get out those eigenfrequencies, what we assume is that the solution for this, for the acceleration as the second derivative of the displacement, is an harmonic solution. And this is the simply the template we insert into the equation, and what we get out is this kind of a matrix equation, where we as a solution get on the one hand side this vector u, which is the eigenvector of the equation and which is represented by the eigenmodes in our application, and we get the eigenvalue, which actually represents the eigenfrequency in our application. And this is already, I think, enough from the theory part, but at least that we know what are we looking into. And now I want to show you what the frequency analysis has of a benefit for us. So eigenfrequency, I explained that. That's the natural vibration of those structures. If we now load our structure with a periodic force with that kind of frequency and a similar style, so actually if the eigenmode displaces the geometry in the set value and we apply that load in the exact same direction, then there is simply a high chance that we have very large deformations, and depending on our material law, we will have failure here, or we might have a very annoying sound or a noise that comes from that we want to actually prevent. So the eigenfrequencies already tell us a lot about what we actually want to do, and show us what we can achieve. And it is the base actually for two other kinds of simulations, where one is the harmonic analysis, where we actually want to test, as I said, the loading, a periodic loading for a complete frequency band. And you can see on the right in this small image that this high peak is actually one of those eigenfrequencies, where the displacement or the magnitude, the structural response of our body is just the highest, and we have a high chance that we get some problems here. So let's say we have an engine that starts up and we know this engine would work perfectly fine once it's on his working frequency, but when we want to start it, actually we have to make sure that the basement or the bearing of this engine does not have any problems within this frequency band that we want to start. So there might be that that it starts vibrating heavily and we have a breakage here. Or we might have, for example, in a car, that when we open up the top window of the car, via the wind that gets into the car, it could be that the car trunk simply starts vibrating. That is very annoying for the driver, and that's why we have to prevent that behavior. And we can actually act by changing the design. Same as for structures like if we have buildings and we have wind loads, we want to add there a vibration damper that helps us to cut down the vibrations on the frequencies that can be introduced to the building by an earthquake or via a wind load. That is simply how we want to act design-wise onto those challenges that the nature actually places onto us. And the second one I just want to mention here is that based on those eigenmodes, those eigenmovements of the structure, you can also assume that the displacement you have in a dynamic analysis can be somehow created when we do a superposition of all of those different eigenmodes. And of course we can only we cannot calculate an infinite number of eigenmodes, but it is simply that up to a certain degree you can measure on how accurate it becomes. So of course it's an approximation, but it's from the computational costs, it's really less effort. So it's very likely that you at some point want to simply do a first step into the direction and do a modal dynamics analysis of your structure. Okay, so let's look at the case we want to do. Mattia introduced the geometry, and what we actually want to do is, in this case, we really simply want to fix here now the face on the bottom. So this should not be capable of moving anymore. That's the only boundary condition we want to introduce. The rest is totally free. And what we want to get out of this is simply the frequencies where the eigenmodes actually happen, and we want to know the from those eigenmodes how they actually look like, so that we can understand what would happen here. How do we need to react on that via our design? We have one basic fan that we will base the simulation on, but we will want also to look into the fan variants and then simply compare the results and look at what actually we should use now for our part. Okay, so we're gonna go now to SimScale. So this was shown, I think, as well beforehand. This is now the starting point to us, where we can get via upload our geometry inside of the SimScale workbench. We can choose a step file, and we can simply take the step file that we exported from CAESES. Good, so let's now switch to our browser. As you can see now, I will simply go to SimScale. Go here to community. You see here's the forum and the public projects, and we will click here on the public projects. And just as a quick hint, you can see here now there are all kinds of different simulations, and that's what I mentioned in the beginning as a template. You can have a look at that. You can start from that. Maybe you're really interested also in other applications. And what we also have here is the forum, where a lot of the knowledge of this community is bundled. And what you can see here is simply that we have here a CAESES and SimScale webinar section. And if you go here, you will find already here the description for our homework. So if you're interested in doing it on your own, you can also have a look here. So I will now switch to my dashboard. And I prepared a case for us so that we can have a look at the frequency analysis setup. So I open now this project in the workbench. So this is the environment where I will be working and setting up my results. The part beforehand was the community part where it's presented and everybody can have a look. So this is now our fan geometry. It's loading right now, and we have here the thing in our 3D viewer in our browser. And what we want to do is, first, to get it started, we want to create a mesh from this geometry. Without a mesh, we cannot run a simulation. So what I want to do is here, I either click here with a right click and say create new mesh, or I click mesh geometry. And it opens up here the field where I can see all the different algorithms that are possible to do it. And for us, it would be right now simply fine to quickly start that mesh, because it has some default settings. You always want to start with a very coarse mesh simply to see if your setup is even the one that you want it to go, and then you will refine your mesh and see if the solution for all of those different meshes will converge to a constant value, and then you know, okay, this mesh is what actually I want to use for my parameter studies or similar things. I also have here the two different variations which I can have a quick look at. So this is the one variation from Mattia, where you can see here, this is here quite thin, while if I open up variation number 2, this is a thicker part, and we can already expect, as this will be stiffer at those parts, that the frequencies of this might increase. You also know that from materials that are stiffer, that if you now hit them and see the vibration, it will be on a higher frequency. Okay, so what we now need to do is simply start this mesh, and what we will get is a mesh that looks exactly like this here, where we see, okay, this is now a volume mesh, and we can now, based on the nodes of this mesh, start a finite element analysis on this. Okay, I will create now a new simulation. The setup of such a simulation is quite easy and quite fast, so probably it only takes 2 to 3 minutes. We will use fan eigenfrequencies, create a new simulation. I have it here. Now I have the possibility to choose here in the solid mechanics section to choose frequency. Could also use harmonics. That is what we planned for the homework. And you already see those peaks again at different frequencies. And now we want to know those frequencies. We want to get the eigenfrequencies and the eigenmodes. So I save this analysis type, and now dynamically on the left side the tree expands and we see what we actually want to do. So we go to the domain, we use the fan mesh. This mesh is not finished yet, so I use my old one for now. I save it, and now the domain for my simulation is clear. It's our fan that we want to look into. Great. I do not need to define contacts here because I only look at one geometry model, so I go directly here. I will disregard gravitation for this model. Just one could simply set it up, but I just go to the material section. Now I have to define what my my fan is made of. By default, this is the properties of steel. You can take any other property by just clicking on import from material library, take the material you want, and as we only have one body here, we will simply click here and save this, and the material is assigned to that body, and we're good to go here. As I mentioned, on the bottom of the part, here, the now red highlighted section, we want to add a constraint boundary condition. So this should not be allowed to move. That's why I click here, I add selection from viewer, I save it, and this is fixed now. I don't want to apply a load because I want to see the fan simply like it is without any load. I also did not add any gravitation in the beginning. And now the only thing I have to choose in the end is how many of the eigenfrequencies am I interested in, because it might be a lot of them. And it also depends on the mesh size, but normally I'm only interested in the lower ones. So I can choose here 10, 100, whatever. It will take the lowest eigenfrequencies within the range that I define below. So in this case, I can choose here lower frequency limit is 0, and then I have 100,000. So I definitely, for this geometry, will get out my 10 eigenfrequencies. The last point that needs to be done is now I can check on my simulation. It will tell me that this is not carried out now in parallel, but we also do not need to do this for now. And I will simply create a run here. Checked again. Name it run 1. Take the default setting, and now I need to hit start, and it will simply start here on the bottom. You see the job status I run, which will result into solution fields that we can look at. And as I have to speed up a little bit, I will simply show you what comes out of this analysis type. So what we get is a frequency plot that shows us all the eigenfrequency values for this setup. And as you can already see, we have 6 eigenfrequencies, one after another, that are kind of the same level. So the first one here is at 1,600 Hertz. Above we have it at 5,400 Hertz. So this is quite interesting, and this is simply because those blades, we're gonna see it in a second, have their eigenfrequency for every of those blades simply at the same point. I mean, this is clear to us if we think about it, because those blades are simply the same. They are just a rotation around it, so it makes sense that they have the same eigenfrequency. And now let's have a look at the eigenfrequency itself. I will just introduce quickly the post-processor, and then we'll switch back to the slides where I can give you a super short summary on that. So we see here it automatically loaded the first eigenfrequency. We can see here this is the displacement field. A red color means this is a very high frequency, a very high displacement, and that means for this eigenfrequency we're looking right now at, everything is blue except for this blade, meaning, okay, obviously this blade would now vibrating. If I would go to the second of those modes, we would see another of those blades simply vibrating. And based on that, we can decide on, do we have to do a design decision on that? Do we have to change something? Okay, let me switch back quickly to our slides. Give you a last quick summary on the results. Exactly here. So I put here the different variants that also Mattia provided me with. We have the fan I showed you. We have the 2 fan variations where the second one had that thicker part at the blades, and where we can already see, okay, this leads to the exact same plateau of 6 eigenfrequencies, but they are on a higher level for each and all of those eigenmodes that we can actually see. Second part, this can be also done in the post-processor. I think we lack the time to do that right now, but you can simply see here the animation of what is actually the eigenmode. What does the eigenmode look like? And the first one, of course, just one blade vibrating. when we go to eigenmode 20, so I did an analysis of 20 eigenmodes, we see that this is already the complete structure more or less is involved in this eigenmode movement. So the last thing I want to show is the harmonic results, because this is also what we planned for you if you're interested in the homework. And this is what we can see. We said that the first eigenfrequency or the first 6 eigenfrequencies are at the level of 1600, and here we have that high peak. If we test with a load on the blade with a periodic load, we will get a high peak of amplitude at this frequency. The same we have for the second and third. The interesting part is we loaded here with the second eigenmode movement, so this is kind of a twisting movement. That means we have a high peak here, and at the third one it's around 8600. We just have a very, very small peak here. You can see it's slightly turning up, and that's simply because of the fact that the load that we applied corresponds with this eigenmode and not with this eigenmode. Exactly. So if you have more questions regarding that, please look into our forum, look at the step-by-step tutorial that we provided here. You find here all the information about how to set that up. We have the project here for you where it contains already one geometry, saying just one geometry, because Mattia will actually tell you or told you already how to export those different variants. So you can use this as an input, upload it as a step file and try your own modifications of the geometry. And here you find the step-by-step instruction. And I think Mattia will give you a quick hint again, also on the point in the forum at CAESES where you can find all the information you need.
Exactly. Yeah. Also on our forum, so if you go to our website, www.caeses.com and navigate to the forum, then in the forum, in the modeling section, you will find a thread about the fan model that I presented. You can download the model, and there is also a link that will guide you through to the download of the free version of CAESES, so that you have, of course, also the tools to use the model. And yeah, if you have any questions then that come up while doing that, then you can ask us in the forum.
Exactly. Great. So that's also why I want to show this slide. So please feel free to reach out to us in any cases if you want to have information about how to do those geometry modeling, how to do the simulations. Also, if you're interested in other parts of those two tools that we introduced to you, feel free to ask us. And from our side, this is, I guess, the end of the presentation. Thank you very much for listening to that part, and if you're interested, please contact us.
Yeah, thank you also from my side, and this was the last webinar of this series, so watch out on our event pages for CAESES and SimScale for future events. Bye-bye.
Great. Bye.